Now I can't even go before because the real exams
Because Monday, Wednesday, Friday, I'll be at work. Monday, Wednesday, I'll be at work from
Okay. Let's get started. Just so everybody is clear, this is the last topic lecture for exam 1. Okay? In other words, exam 1 is going to be everything that we've covered from day 1 through what we covered today. Okay? So today's lecture is going to be a topic on exam 1, but Wednesday's is not. Okay? Because Wednesday we're discussing the project, the class project. That's what we're talking about on Wednesday. Okay? So Monday, today, Truss deflections. Wednesday, the project. Friday, we do exam review. Okay? And then Monday, we celebrate. Okay? So just to be clear, okay, you have a homework that's due Wednesday. Afterwards, that's the last homework until next week because you've got the project and then you've got the exam coming up. So you're getting a little bit of a reprieve on assignments because you've got a celebration coming up. So everybody okay with that?
So we don't have one that'll be due Friday?
No.
Okay.
No. You will not have a homework Wednesday due Friday. You will not have one Friday due Monday. You will not have one Monday due Wednesday. But on Wednesday, you'll have an assignment. So you get like a week off. Unless you want one. That's what I thought. Okay. Are there any questions? Everybody get the code? All right. And, in terms of grades, everything's, I think, fairly up to date. I think 3.4 was still being graded as of yesterday. But everything before that is taken care of. Attendance is taken care of, grades are taken care of, and class as a whole doing phenomenal. So I'm tickled. So with that, let's get into our discussion today. Okay. So if you recall, I think I maybe blew your minds a little bit last time with all this energy stuff, right? So the idea was that we're going to be solving for deflections, and the way that we're going to approach deformation problems in structural mechanics is to use an energy approach. In other words, we compare the external work done to the system against the energy that it stores, much like Link in Zelda drawing the bow. Link does external work to the bow by moving the arrow through a given distance, so applies the force through a given distance. That's the external work done. And then the bow stores energy, because when Link lets go, the arrow shoots, right? So if you can compare those two energies and set them equal to one another, you can solve for the deflection. And that's basically what we're doing. Now the problem with a direct energy approach, which is what we had on the last slide and what we talked about last time, is that that's great if you have a system with a single load on it and you are interested in finding deflection where that load is. But that doesn't really happen a lot in structural engineering. In structural engineering, we have loads all over the place, and we want to find the deflection right there. Okay? So the way that we handle that is we preload the structure. We put a fake load where we're interested in finding the deflection, and then we add on top of that all of the other loads. Okay? And if you remember, we called that P1 and P2. So P1 is that fake load, P2 are the set of all the real loads. And so when we do that, we separate all our energy components and we say, okay, let's only use the ones that really matter. Because if all the external work done equals all the stored strain energy, then each of these components equal, like W1 equals U1, W2 equals U2, and so on and so forth. And so we'll only use W2 and U2 because those are the ones that are most useful. And so what we get is our fake load times the deflection that we're actually interested in equals this. And so since this fake load can be whatever we want it to be, because we're using it just as a means of tracking the energy, we'll set it equal to 1. And that's the method of virtual work. So a lot of what you're about to see here in the next few slides is just a rehash of what we did on Friday, or what we discussed on Friday. But we're going to put it to practice with a real example here in a bit. So, what do we do with the method of virtual work, or what is the method of virtual work? It's also known as the unit load method. It's an energy-based method for computing deflections. Okay? We're going to start with truss deflections, obviously, but when we start looking at beam deflections and frame deflections, we're going to use the same approach, the same idea, the same unit load method. The mechanics of applying the unit load method to beams and frames is a little different because we've got to break out some integrals, but the idea is the same. The underlying concepts have not changed. So how does it work? We start off, this was the illustrative example we talked about on Friday. We said, all right, let's determine the vertical deflection at B. Here's the truss. It's a regular old structural analysis problem like we've seen this whole semester. The only thing that's different is I'm giving you more data than I did before, okay? I'm giving you the area of each member, in other words, how big around they are, and I'm telling you that each member is made of aluminum. And that's important because I'm giving you the E value for aluminum. So what I have done for this truss is I have defined not only its geometric section properties, but I've defined its constitutive properties as well. I didn't do that before because for statically determinate structures, it does not matter if the truss is made out of steel or concrete or popsicle sticks. It doesn't really matter. As long as the truss is determinate, the forces in the members and the reactions are independent of what the truss is made out of. But that's not the case with deflections. I mean, think about it like this. If I made a truss out of steel elements as opposed to making a truss out of rubber bands, it's going to deform differently, right? The deformation is going to be different. That's what we're talking about. We're talking about deformation. So we have to be more precise in our definitions. So how does it work? The first step that we do is we solve the truss. Now, we've already done this problem. We did this problem a while back. So these numbers that you see here should be familiar. This was a truss that we solved in a prior lecture. So we've already done this before. I'm going to call these the real forces because these are the actual forces present on the structure. And I'm going to denote real forces with a capital F, okay? Then what I'm going to do is I'm going to kick all of those loads off the system, and I'm instead only going to apply a single load. That single load has a magnitude of 1, because remember, we can choose the magnitude whatever we want, and 1's the easiest number to deal with, because anything times 1 is itself. I'm going to place that load on joint B. Why am I placing it on joint B? Because that's the problem. I'm interested in finding the deflection at joint B. I'm placing it vertically because I'm interested in finding vertical deflection at joint B. Now I'm placing it downward. I'm placing it downward because if I go back to the original problem and I look at the loads on this truss, I kind of think that when it's all said and done, joint B is going to deflect downward. So I'm going to take that fake load, which I'm going to call a virtual load, I'm going to take that virtual load and apply it downwards. If I get a negative answer at the end of the day, that just means I'm wrong. And that just means that it's deflecting upwards, okay? Everybody all right with that? Same kind of idea as what we've done before, right? So far so good? All right. So I solved the truss. Solve the truss again. That's the only part that does kind of suck with deflection problems is that they are labor intensive, okay? So I'm sure somebody's asking, well, what about an exam? Don't worry, the trusses in this regard will be manageable. Trust me, I know what I'm doing there. So we apply the load, solve the truss again. And so we get a new set of internal forces in the members, and I'm going to call those little f's. The little f corresponding to the virtual forces. Now, a couple things about the virtual analysis. Number one, does anybody notice how the structure is symmetric now? It wasn't symmetric before, but it is now. So this member equals this one equals that one, this one equals that one. So if you can exploit symmetry, you can make your work a lot easier, right? By only solving half the structure, okay? Also, while it isn't true in this problem, it is going to be in our example, is that if you're removing a bunch of loads and replacing them with just a single load, You might have 0 force members. Maybe you didn't in the real structure, but you do in the virtual one, okay? So if you can identify some 0 force members, you can make the analysis go real quick, okay? And we're going to see that today with our example. So just something to keep in mind. So you've got, for every member in the truss, you've got a set of real analysis results, which we'll call capital F, and you have a set of virtual analysis results, which we'll call little f. Now, big F, if we're talking about US units, big F is usually measured in kips, and little f is unitless. When we put that 1 kip load, it's not 1 kip or 1 kilonewton, it's just 1, okay? So it doesn't really have units, okay? So we're gonna call that big F and little f. By the way, your textbook calls this F and F sub V, but it's same thing, so, for virtual. So, the next thing we have to do is just compute that. Just little f, big F, L over EA for every member. So set it up in a table. Little f, big F, L over EA. Little f, big F, L over EA. So by the way, what software package would be very nice for this? Excel. It's a very tabular friendly computation. Now, the terms that go into this are your E value, which is in KSI, and your area, which is in square inches. So notice, I've got kips, no units, kips per square inch, square inches, and then I've got the length of each member. What units should I use to describe the member length? Inches, okay? If you look at the problem, the truss members are described in feet, okay? But this isn't feet, these are inches. Okay, and the reason we're using inches is so that the units cancel out. So you could argue that there's a conversion factor that we have to apply at 12. We're going to take all of our lengths and multiply them by 12. Okay, we're going to do that today as well. I just want you to see that the lengths are in inches, and that's why. Okay, does that make sense? So set it up in a table. Here's my L values. Here's my E values. Here's my A values, corresponding to each truss member. So just be a little bit organized with it. We're going to put the little f values here, big F values here. Typically just put tension as positive as long as you're consistent. You can actually use compression as positive, but customarily we always use tension. So if there's a negative value, that just means that answer's in compression. And then for each row, bam, 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 divided by that equals this. That times that times that, divided by that equals this. And so on and so forth. And you get some values, sum them up, and that sum is your deflection. Point blank. Okay? So, to summarize, because we got a positive answer, and because we took care of our units, I propose that joint B deflects 0.237 inches, and it deflects downward. And that's how you do it, okay? So I want to take a step back and just make sure from a concept standpoint that the idea makes sense. Is everybody okay with the general idea of what we're doing here? Everybody good? So if that's the case, let's look at our in-class example. So this is what we're going to do in here. So we are going to determine the vertical deflection at joint C, and we're going to determine the horizontal deflection at joint B, or this truss, okay? So I'm just curious, how many truss analyses are we going to have to do to fully solve this problem? 3. We're going to have to solve the truss as is, and then do 2 more, right? One with a vertical load at C, and one with a horizontal load at B. Everybody okay with that? Okay. We're going to assume that every member is made of structural steel, so the E value is 29,000 KSI, and I've got the cross-sectional areas listed. And just to keep it simple, all the horizontal and vertical members have 2 square inches, except for the diagonal, it has 1.5. This is 6 foot, and that's 8 foot, so that makes this diagonal at a 3-4-5 slope ratio. Everybody okay with that? All right. So here's what we're going to do. All right. So I want to try and keep this organized. Okay? So if you don't mind, what I'm going to do is this. I'm going to put the real structure over here, and then I'm going to put a virtual analysis over here. And what we'll do is we'll do the vertical deflection first. So we'll say we'll do that. Okay. So I'll try and not write too tiny, but you'll see what I'm doing here. Okay. All right, let's see. Okay. All right. This is okay. All right. Let's see. In terms of boundary conditions, we have a roller here. And we have a hinge right here. Okay.
I think you got C and D swapped.
I did?
Yes.
You are 100% right. You are 100% right. Okay. Let's see. Is there any zero force members in this truss? May see one. I see one. I actually see two. AD. You are right. But why'd you say that?
Because if you look at joint A, there's only a reaction going left to right.
There you go. So, there you go. If there's a force here going horizontally, that's got to be the same. What's going on there? Nothing. So this is a zero force member. By that logic, somebody else, anybody see any other zero force members?
DB.
DB?
Never mind.
I don't know about DB.
And
I don't know about AB. No, not AB.
DC.
I don't know about that one either. What about the? What about joint C? What do you see on joint C?
horizontal load.
There's a horizontal load, which means this member is going to carry that horizontal load. And what's going on here? Zero. This is a zero force member. Bless you. Tell you what, let's see if we can add to our analytical discussion. Can somebody tell me what is the horizontal force inside member CD?
60 kips.
60 kips in what?
Compression. What?
Is it compression? I think what's going to happen on joint C? I think about it. Here's joint C. There's 60 kips, right? This is 0. So what's going on here? 60 kips, so it's in tension. Does everybody see that? So this is 60 kips in tension. So let me ask you this. Is solving this entire truss really that scary? You see what I mean? Now let's start identifying some reactions. So I have a reaction right here. I'm not going to draw arrows yet. I have a reaction right here. We'll call that AX. I can do better with that. I have a reaction right here. We'll call that DX. And a reaction right here, DY. I've got 2 horizontals, 1 vertical. Maybe what I ought to do is solve for the vertical first. What is the vertical reaction going to be?
80 kips.
80 kips going up because I've got 80 kips going down, right? So if I do that, I mean, if I sum forces in the y direction, that's what I'm going to get. Okay. Now, how should I solve for the remaining reactions? Maybe what I ought to do is sum moments. What do you think? Should I sum moments at D? If I sum moments at D, I'm going to eliminate dy, dx, and that one, right? That one's going to be gone. So maybe I can do this. Maybe I can scooch this over just a bit. I forgot you. You go back there. All right. And I'm going to sum moments at D. And what am I going to get? I'm going to get, let's see, I don't have to worry about that, don't have to worry about that, don't have to worry about that. I'm going to get 80 kips times 6 feet, right? So 80 kips times 6 feet. Has got to be balanced by AX, right? AX, so if 80 kips is rotating it like this, AX needs to rotate it the other way, right? So I propose that AX is going in that direction. So if 80 times 6 equals something times 8, what is that something? 60, right? So therefore, so if AX equals 60, by the way, what's DX? Is it? Is it 0?
Oh, no, it's 120 to the left.
It's 120 to the left because I've got 60 and 60, so that's got to be 120. Did everybody see that? Bless you. Now, by the way, if the goal is to solve for the entire truss, how many members am I missing right now? 2. Can somebody tell me what is member AB by just looking at it?
60
60 kips in compression. Because if I analyze joint A, this is going like that, this has to go like that, right? So this is going to be 60 kips in compression. And in fact, the only real analysis that we need to do is for joint B, right? That's the only one left. Let's look at joint B. Here's joint B. We have 80 kips going down. What's the deal with the vertical member? 0. What's the deal with the horizontal member?
60 kips to the right.
To the right, yes. 60 kips to the right. So all we have left is this diagonal. So which way is the vertical going, up or down? Up, and what is it?
80.
What about the horizontal? Which way is it going, left or right?
Left.
And how much is that? By the way, does that 80 and 60 comport with the slope ratio of the diagonal member? Yeah, because it's 6 to 8. And so if we solve for that, $60 squared plus 80 squared, square root is 100? 100 and what? That truss is solved, isn't it? We're done. Not too bad, right? I mean, you tell me, is that pretty straightforward? So, any questions on that? Okay, yes?
And you don't need the reactions when you are solving for the deformation, the final deformation? Like you won't need that later?
No, that's a good question. So will you actually use the deformation or the reaction values in the method of virtual work? No. Now, that doesn't mean you don't need them to compute the member forces, which you will use, but no, you don't actually use the reaction values later. Any questions? Before I move on, one thing I'll add to that, when we start doing shear and moment diagrams and start looking at deflections and beams, the reactions may be needed to define moment functions, but we'll get to that later. So. Okay. Sound good? All right, now, let's do this truss analysis again. All right, so what are we going to do? So we're going to analyze this truss all over again. But what I'm going to do is instead of analyzing the truss for the loads that were originally present, I'm going to kick all of those loads off and I'm going to place a single load on the truss. That load is going to have a magnitude of 1. It is going to be vertical and I'm going to place it at C. Why is it a vertical load at C? Because I'm interested in the vertical deflection at C. Okay? So I'm going to have just a single load of 1.0. Now, my question is, would you like me to place that load upwards or downwards? Downwards. Okay? Okay. So now we are going to analyze this truss all over again. Okay. And then likewise, we're going to have a reaction here and a reaction here. I'm going to assume those in the same direction that I have over here. So we'll call this AX and DX. Sometimes I'll write these in lowercase letters just to, like, as I'm doing the problem to remind myself, I'm doing a virtual analysis right now. And then we'll do DY. Let's start chipping away at some things. Any zero force members in the virtual structure that you think you can identify right now? I'll give you a hint. Any zero force members you think you can identify by investigating joint C?
CD.
CD. Because this is a vertical force. Vertical force, this is 0, right? So again, this is interesting. This was not a zero force member over here, but it is over there. Because the loads have changed. Very possibly can happen. By the way, anything else you can tell me about joint C? If this is 0, what's this?
1 in compression.
1 in compression, right? So this is going to be 1 kip in compression. Not 1, actually I said 1 kip because it's sort of an easy way of thinking about it, but really it's just 1 in compression. Any other zero force members pop out?
AD.
AD. That one's a zero force member as well, right? For the same reason that it was a zero force member over here. Reaction, reaction, so on and so forth, right? Make sense? We also have member AB solved. We know that it's going to equal AX. We just don't know what AX is yet. We got to some reactions or solve for reactions to get that. Speaking of, let's look at those reactions. Any reactions you think you can identify right now?
DY.
That's 1.0, right? My apologies if the writing's a little tiny. I wanted to put everything on the same screen. So what do we need to do? Maybe some moments at D again? So if I sum moments at D, I don't need to consider this reaction or this reaction. What do I have? 1 times 6 equals something times 8. Is that right? So what is AX?
0.75.
Oh. Three-fourths, right? And if that's 3/4 to the right, what's that?
3/4 to the left.
3/4 to the left. So what does that mean? Remember AB, 3/4 in compression. And it looks like, again, the only thing we have to solve is joint B. So let's see what happens with joint B. Oops. So, are there any external loads on joint B? No. There were over here. Now there's not. Okay? We have a 1 going like that. We have a 3/4 going like that. So what do we have? A vertical and a horizontal. So the vertical is 1. That's 3/4. So they're both in the right direction. They both comport with the slope ratio. So what is BD going to be now? Five fourths, right? And that's in tension, right? Okay. All right. I knew I threw a bunch of stuff at you and we did this really fast, but hopefully the truss analysis, while it was a little fast, was manageable. All right, does anybody have any questions about what we did? Everybody good so far? Okay. All right. Does everybody have this here on the board? Okay, so now what we can do is we can apply the method of virtual work. And what is the method of virtual work say we've got to do? That if we want to determine the vertical deflection at C, we sum up the following. The little f, big FL over EA for every member, okay? Now, as I said, this is a calculation that loves to use what software package? So let's do that. It's almost like I was ready for this. Okay. So by the way, what member or what unit should I put length in? Inches. Okay. So this is going to be my table that I set up. Let's see. The 4 members that I have in the truss are, so I've got the horizontal members, I've got the vertical members, and I have my diagonal. Okay? All right. Let's do the easy values. What was the E value for every member?
29,000.
Okay. What about the areas? They were all 2 except for the diagonal, right? The diagonal was 1.5. Okay. All right, what about the member length? What are the length of the horizontal members? So
72 inches.
what about the verticals?
96 inches.
And what about the diagonals? So if you want, you could do it like this. You could say 12 times square root. You could do that. Just do the Pythagorean theorem, multiply it by 12, get 120. Okay. So far, so good? Okay. So let's start off with the real forces. Somebody help me with that. What was member AB?
60 pips.
In what?
Compression.
So,
96.
okay. CD.
60 pips.
In, so positive 60. What about AD?
0.
What about BC?
0.
What about BD?
100 kips in tension.
So positive. Okay. Okay, what about little f? What was AB?
0.75 compression. Negative.
Okay, what about CD?
0.
What about AD? What about BC?
1 compression.
So,
Negative.
and this one?
1.25 in tension.
Okay. Pretty simple, right? So what do? For each row, little f, big F, L, divided by E, divided by A. So you can do that, or you can put it in parentheses and give you the same answer. And then just copy that down. A lot of them are 0 because either the real or the virtual force is 0. And then sum it up. And then what I like to do is, I don't like to go more than 3 decimal places. Okay? So what we'll do, put that in there just so we have it for posterity. That right there. And we get and what are the units, by the way?
Inches.
And which way?
Down.
Because we assumed downward displacement, and that's what we actually got. And we're going to do the horizontal one here in a second. It's a lot easier than you would think. All right, any questions? Okay, first off, so this is for the vertical deflection. What's going to change for the horizontal deflection in this table of values? The little f, right? So what I'm going to do in Excel is I'm just going to say, let's just like do this again. Let's just delete those. And then when we solve the vertical or the virtual truss again, we'll just put those values in right here. Does that sound good? Okay. Now, what was the goal for the horizontal one? What was it?
Find the horizontal deflection at B.
At B. Okay. So, all right, I'm going to take this keyboard off again. Okay, so here's what I'm going to do. Okay? I am going to assume that the truss will deflect in such a way that joint B will deflect to the right. Okay? So I'm going to put a horizontal load of 1.0 right here. I'm going to give you a spoiler alert. That's wrong. That's actually not correct. It actually deflects the other way. But let's see what happens. since we've got a class coming in here in a little bit, I'm going to walk you through a couple things. Somebody tell me what's going on with these two members. 0, right? This is 0. That's 0. Okay? Now watch this. Would you agree that that's 0? So if I do, let's see, okay. Well, let's hold off on that. If I sum moments at A, this is going through A, that's going through A, I propose that this is 0 as well. In fact, the only reaction in this entire truss is that. Okay? If I look at joint D, I have no forces going through joint D. That's 0. These two members are framing through joint D, and there's no other loads. These two are 0. And in fact, the only force in the entire truss is that one right there. That's the only force. Everything else is 0. So, if I go to Excel and I say, let's make this 1, and make this 0, there's my deflection. Notice how this comes out as negative? It comes out as negative because my assumption was wrong. I assumed right, got a negative answer. It's going to the left. That's all that means. Let me take a step back and see how we're feeling on this. I know I did that truss kind of quick, but there's not a lot going on with it. Anybody have any questions? Yes.
On the exam, when we do this analysis, are we doing it by hand or Excel?
Yes, you're doing it by hand. But I'll talk about this on the exam review. I'll most likely give you a table so that you don't have to draw all that out. I'll try and make that stuff easy for you.
Thank you.
Do you want to, can we just put solve in Excel after we've done all the work before that? Or do you want us to,
Solve.
for the homework, I mean, solve in Excel?
So, okay, let me just say real quick about the homework. I have no problem if you upload both your hand calcs and an Excel sheet.
Okay.
As long as the Excel sheet is neatly formatted. Don't make it a mess.
Do
So,
we have to have like the FLEA, that one
yeah,
calculated, or can we just do it in Excel?
you can do it in Excel, but upload your Excel sheet.
Okay.
Yeah, you can do that. But make sure it's easy to follow, that the TA is not having to, Sound good? All right, I'm going to pull up the code one more time in case everybody got it, but that's all I got, everybody.